I'm Casey Honniball, and you're watching the Break It Down Show.
If I call Casey Stacy, it's because I'm a dummy and my brain will not give it up. So just in general, everybody should know that. It's to start this thing. Yeah, but Casey is brilliant, by the way. I'll put her bio at NASA's webpage up here in a second. But she and her team of researchers were the ones that made that announcement about there being water on the moon. So I thought we would get into more of the nuts and bolts, because it's one thing to say that, but it's another thing to understand what it is. And then, just so you can understand how smart Casey is, let me read to you the title of one of her recent, and you have had a busy 2020, 4 published articles. Wow.
Yeah.
Using, let me see here. Okay, I got to get this right myself here. Using the spectroradiometric performance of an uncooled mid-wave infrared hyperspectral interferometer using a microbolometer array detector is one of her articles.
Yeah.
When you say that to your folks, are they like, please? I mean, did you ever watch Gilligan's Island as a kid when the professor would say stuff? This is harder than that.
My parents think I'm a rocket scientist.
And are you?
No, I'm a planetary scientist. I don't work on rockets. Those are actually real people.
Yeah, and there's a great interview with you when you were at University of Hawaii doing, I guess, your doctoral study, and you guys had this giant telescope that floated from a balloon that was it as big as a football stadium. This balloon.
Yeah, so that was actually work I did as an undergrad at the University of Arizona, and I worked on it's a terahertz observatory. And like you said, the balloon is the size of a football field. We launch it from Antarctica at the U.S. base McMurdo, and it takes this telescope all high into the atmosphere so that we can get above the atmosphere, so we can look at these lines that we can't see from the ground.
Right. Yeah, and you're studying these things using non-visible light waves. I guess you were saying radio waves is the same. All of those fancy words. Is that the same thing you're doing with NASA now? Is getting up high into the atmosphere and studying things like the moon and everything?
Yeah, it's very, very similar, except for instead of it being a balloon, it's actually on an airplane that's been modified to incorporate a telescope. And if you look at the electromagnetic spectrum, there's the visible, the infrared, and then radio. Where I was at the balloon, looked at the radio very, very far away. Whereas now I look at the infrared, which is a little bit closer to the visible spectrum and where your body emits heat.
Okay. And you wrote all 4 of these articles. Is this all based on the same work? I'm actually a peer-reviewed published author myself, so I know that you can take the same piece of work and break off pieces of it because it covers a lot of ground. Is this what happened, or are you just like a super author?
So this work, all of them were published in the same year, but all of them were done over many years. So okay. The first one, the one that you said the title to, was an instrument that I built as a graduate student at the University of Hawaii, and it was to measure volcanic gases like CO2 coming from the Kilauea volcano on Hawaii. The other papers use 2 different telescopes to study the moon and look at water and hydration.
Okay. So you are just a super author. It takes, just for the audience, it takes forever to get through the peer review process. And what you do, correct me if I'm wrong. So the way I understand how peer review things work is you can challenge, add to, or discover, right? Those 3 things. Are you really you're inventing instruments. Are you expanding the knowledge, or are you building on what's already there? How would you characterize it?
So it depends on which paper you're going to talk about. The one with the instrument, I was building a new instrument to show that the technology could work in the wavelength range that I wanted to use it for, and provide scientifically useful data that could be potentially deployed to a space telescope. The other 2 papers, one of them, the molecular water discovery on the sunlit surface of the moon, that was a discovery. That was expanding our knowledge and bringing up new questions that we didn't know we were going to have. And then the other paper was expanding our knowledge based off of things that had been done prior to the work I did. So it was saying, okay, this is what we see, but I'm going to take it a step further. So it really depends on which paper we're going to talk about.
And again, in the academic writing field, you have to be very specific. You're not just talking about a piece of the puzzle. You're talking about like the laminate on top of the cardboard that is a shade of blue. Like it's very, very, very specific. Even in your paper, as I read the abstract and try to hang on for dear life as I do that, it appeared that you were talking about you couldn't conclusively say it was H2O. It might be some other form of water. Can you help us understand what the heck that even is?
Yeah, so what I was looking for in the NASA press release a couple weeks ago was molecular water, the water like we know and love and drink every day, so H2O. But prior to that, we couldn't distinguish between water and its close cousin hydroxyl, which is just an oxygen and a hydrogen. And this was because of the wavelength range that we were using. Once we discovered this new way to look for water, we employed that using on the moon using the Stratospheric Observatory for Infrared Astronomy, SOFIA, the airplane. And we were able to make the actual detection of molecular water without confusion from its close cousin hydroxyl.
All right. I took biology and chemistry in high school, and I know that, H2O works because H and H has two little springy things that go on, and you can put one O on it. The H ball, right, in class had two holes. So if there's two holes, how do you have HO? Does H just attach twice? How does that work?
Yeah, it actually attaches to other cations in the surface of the moon. So if there's, let's say aluminum was on the moon, it would, or sorry, not aluminum, silicon was on the moon and it attaches to a silicon.
Okay.
Yeah.
So it's kind of a dummy almost. And then no.
It's just like, it's like the oxygen and hydrogen are bound together. And then this little molecule attaches to a bigger surface grain on the surface of the moon.
Got you. And then is that useful in terms of creating water because you have most of the, okay, so you can still turn it, but it's an extra process, I imagine, to turn from HO into H2O.
Yeah, so HO or hydroxyl is produced on the surface of the moon because solar wind implants hydrogen, and there's a bunch of oxygen on the surface already. So there's a lot of hydroxyl on the surface. But then if you take two of those hydroxyls and you combine them together under high temperature environments, like say during the lunar noontime temperatures or during a micrometeorite impact, you can take these two hydroxyls and combine them to make water.
Fascinating. And then I'm going through some of these things because I'm trying to set the stage so we can really have this conversation, because a lot of people have never say the word hydroxyl in their whole entire lives. I've had hydrox cookies, wonderful. Hydroxyl, I don't rub that on my face, maybe, I don't know.
Actually, what's interesting is hydroxyl is the active ingredient in drain cleaners.
Terrifying.
Yes, you won't want to drink that.
Okay, so we know that there's hydrogen there because of the solar winds, and there's not an atmosphere on the moon to speak of, really. So how does oxygen exist on the moon? That's a little bit hard to understand.
So oxygen is incorporated into the grain. So it's if you think about like the Earth, there's a bunch of rocks outside that are made of silica. So these silicate grains on the surface of the moon, when they're hit by the solar wind and these hydrogen atoms, they create a broken bond of the oxygen. So it's free. It's not free from the grain, but it has a free spot for this hydroxyl molecule to attach to. So it's like it's incorporated into the grains.
Okay. Yeah. Okay. That makes sense. So it's like it's dating and hasn't found its other partner yet, and we're hoping that it's hydrogen. Is that right?
Yeah.
Okay. I like it. Okay. And then what is the significance of finding H2O on the moon in terms of like what's next? Because there's so many, we've had a lot of people that talk about space, from, the gravity wells between here and there and all these crazy, there were so many questions and things to get into. Why is this important?
Yeah, so it's actually very important in multiple aspects. prior to this detection, we didn't really think that water itself could survive on the surface of the moon because of the harsh lunar environment. So actually finding it on the sunlit surface of the moon opens up a lot of new questions about why the water is there, how it's surviving on the surface, where is it stored, is it potentially a source of water to the polar regions supplying water ice? But also it's important because if we want to do human space exploration, we need to know what's there and how we can potentially use it. So the observations that I made detecting water is just a small puzzle piece in saying, okay, we know that there's water there now. Now, how much is there? How much is it? How is it distributed across the surface? And can we begin to think about how we might be able to extract it in the future?
And then what was your research question for this paper? Was it to determine if there was H2O versus hydroxyl?
Yeah, actually, that was precisely it, because one of my other papers that I published was looking at hydroxyl plus molecular water, and you couldn't distinguish between the two of them. And so I was always like, well, why don't we know for sure if water is actually present on the surface of the moon? Why is this such a hard question? And so that led us down the rabbit hole of looking for new ways to determine whether or not it's there. And that's what led us to this discovery.
When Nature publishes your paper, right before that, NASA puts out a press release saying, hey, we got something big coming out. How big is this? I mean, give us a sense. Look, and I don't want to say anything bad about NASA because I'm not, but is this because you guys are trying to create attention, or is this a really big, massive leap? Or how would you characterize the level of importance of this discovery?
So it kind of depends on who you are and how important space travel is to you, how important science is to you. But in the lunar community, in the science community, this is pretty large. We didn't think that water could survive, and all of a sudden it's there and we're seeing it. So that alone is really important for us to understand the processes of the moon. And then if you want to do space exploration, you got to know what's there. And if water's there, it's a lot easier to use water that's already there than to bring it with us, because it's really expensive to launch water into space. And then also to create water from hydroxyl is another process that consumes a lot of energy. So having it where you're going versus having to bring it with you is really important also.
Yeah, it's easier to bring up a robot to smash rocks and turn them into something else than it is to carry water. Is water and fuel, it's a lot. Yeah, that's really neat. I love it. Okay, and then because you're a planetologist, how does this inform that part of your brain? I mean, we're learning so much about all these planets. I mean, just recently they talked about a planet that rains rocks, right? That's another discovery. So what do we infer because of this knowledge that you've developed?
Yeah, so I like to think about it as the moon is a laboratory. So because the moon has no atmosphere, or a very thin exosphere, as we like to call it, it allows us to use the moon to study how water behaves on an airless surface, which we can then take and apply to other airless bodies like asteroids in the outer solar system, which could tell us, okay, maybe there's water present at these outer bodies. And how does that inform the way the solar system formed? How do these bodies form? How about exoplanets and other solar systems? Maybe we can find water out there on airless bodies as well.
Then as a planetologist, are you going to try to work on proving this in another space? Like, I don't know, go to whatever other moon, whatever similar. Is that what the idea is, to expand it to another body?
Definitely. So we are waiting right now to hear back if we have more observing time, but we hope to use the Sophia Observatory, the airplane, to look at asteroids to see if these asteroids also have water present using the same method that we detected water with on the moon.
Right, because I guess in theory you could just lasso an asteroid and start to use whatever resources are on it. Is that kind of the idea?
And that's partly the idea, is to understand the resources that are available in our solar system, but also just to understand the processes that are occurring so that we can understand where the water on Earth might have potentially come from also.
One of the other recent studies about the moon, as I was researching this, and all at the same time frame, all these discoveries came out, was how much radiation is hitting the moon. Does that impact this water? Like, is it in some way make it so that it wouldn't be usable, or require an extra step to unradiify it? I don't know what you would call it. But.
So depending on how much radiation is hitting the moon, like, so solar wind, if the solar wind is stronger in a decade than it was a previous decade, maybe that previous decade didn't generate as much hydroxyl that can be converted to water. And then now in this decade where the solar wind supplies more hydrogen to the surface, maybe now there's more water capable of being produced on the surface of the moon. So the strength of the solar wind and the strength of the radiation definitely does play a role. But also what is interesting is that same radiation could also destroy the water. So it's interesting to know the strength of it, so you can understand how much could be produced, but also how much you could be losing as well. And if you see it, well, that means that somehow it's being protected from this radiation and sheltered from the harsh environment on the moon.
More questions. All right. Yeah. Just more machines to create everything else. And then when you say there's water on the moon, are we talking one of the many forms of ice, or what? How is it sitting there?
So instead of it being ice, if you think about literally the molecule of H2O, it's just the molecule attached or incorporated into the lunar grains, but they're so spread apart that they can't form liquid and they can't form ice.
Okay, so you would have to do some kind of distillation process to turn this into water and whatever other products you could get out of that. Is that right?
Yeah, you'd have to mine quite a bit of soil to get a usable concentration of water.
Okay, so I couldn't just put a cube in my glass.
No, unfortunately not.
Not yet. Okay, let's talk about Sophia, because that's an important thing. I mean, this is we've learned so much about telescopes. We had another Nicole on the show from NASA, and she was talking about her observation platforms, tests, and all these other things. Tell us about Sophia, please.
Sophia is the Stratospheric Observatory for Infrared Astronomy. It is an airborne telescope that flies at about 45,000 feet, which is above commercial airliners. And it has a telescope, or actually, I have a model of it right here.
Hey, there it is.
So it's a Boeing 747. And this part of the airplane has been cut out to incorporate a door, which is in this model is showing it as open. And this is the telescope mirror. And then there's a wall right here that has been pressurized so that the crew and guest observers like myself can sit, and the pilots can sit up at the top of the plane while we're observing.
I was trying to get a link ready for Sophia so people could look that up. I'll do that in a moment. My buddy Kirk, who lives in Houston and is super proud of Houston, wants to know, is this a NASA effort, a JPL assisted effort? Who's doing this work?
Yeah, so actually, Sophia is a NASA/German aerospace engineering collaboration. So it's NASA and Germany. And then the work that I did specifically was through the University of Hawaii under a NASA grant. And now I'm at NASA Goddard.
Gotcha. And you're a fellow there, right? Continuing to do research. Okay. Yeah. Help me. I'm always fascinated by the details like this. Where like, okay, I just did this incredible thing that just catapulted us forward all this way, but everybody else is trying to answer similar kind of questions. So how competitive is the time on Sophia, or whatever platform it's going to be? And then how much free reign do you have to, like, you must have so many questions. So how do you get to meter out what you want to look into? I mean, you're a fellow, that your job is to do this, but there's only so much you can do.
Yeah. So time on Sophia is very competitive because it's an airplane. You have to consider it flying, the pilot hours. They're only allowed to fly so many times and so many hours. The crew that operates the telescope. So there's a lot of aspects that go into flying Sophia. And so therefore the time is limited. And then what I'm doing now is trying to answer some of the questions that we raised by detecting water on the surface of the moon. And, it is very competitive, but right now I'm currently the only one, or my team and I are currently the only ones that have the capability to do this. In the future, I hope that this expands so that other people can join in on the effort to map water on the moon, to send a satellite or a rover or an instrument to help globally map the water and understand how much water may be at depth instead of just on the surface like our observations are seeing.
Yeah, right. It opens up a whole barrel of new questions for all across the multidiscipline space exploration canvas, I would imagine.
Definitely does.
So someone at JPL is like, we're going to build a rover now, and then go get funding and then do all that. How does funding work for you as a researcher? Like, do you just get a budget and you spend within that, and also the time? Like, if you're going to build a machine, like a physical machine to do your work, you have to pay for that, and that also takes time. Kind of talk us through that part of it.
So, sorry, don't mind my dog.
That's all right.
I have to propose to get observing time, also funding. And so there's this program called Solar System Observations, which is one that I typically propose to conduct my observations on telescopes, which provides funding to me to do that work, but to also write the papers, to analyze the data, to go to conferences and pay for travel fees, so that doesn't come out of my own pocket.
It's all about money and time, ultimately, right? Yeah, you can answer a lot of questions, but it is great that you have this kind of an environment to study. Do you branch out to the Germans or to JPL, or what are these other houses that help with this kind of thing? Do you collaborate to try to build these machines more efficiently or within other resources?
Yeah, so one of the projects that we are currently working on is a collaboration between NASA Goddard, the University of Hawaii, and also JPL and the Applied Physics Lab here in Maryland as well. And so it takes a bunch of people, especially when there's an instrument involved in a lander or rover or whatever satellite might be involved. It takes a lot of organizations to put this kind of project together and make it come to fruition and actually work in the long run.
And then you talked about a lot of different places. I mean, Maryland to Hawaii. Oh my God, that's like a full day of travel. So when you look at, let me ask you this about Sophia. I want to go back. How comfortable is the airplane? I mean, I'm a military guy, so we get on an airplane, you lay on the ground and you wad your jacket up into a ball and that's your pillow. How comfortable? I mean, this thing is built for equipment. It's not built for people. So how comfortable is it?
So actually it's used to be a commercial airliner. And it was modified. So they had taken out a lot of the seats and actually taken out a lot of the paneling on the side too. So it's kind of cold, but they left the first class seats in place so that you can sit in the first class seats basically when you're waiting for your observations to happen. But then they have these, I guess they're kind of like airplane jump seats, I would say. You have to strap in and buckle a couple times. That's what everybody else, the crew, sits in when they're observing. And I mean, they look pretty comfortable. The size is pretty comfortable.
Is it your airplane? I mean, obviously the pilots are flying it, but is it your airplane when it's your time for research? Are you sharing that time with somebody else, or how does that work?
Yeah, so I definitely have to share the time with other people. So Sophia can only observe one object for a maximum of 4 hours, but the flights last 10 hours. So in that whole 10 hours, you may have anywhere from 3 to maybe 6 or 7 different observing programs, so that everybody's looking at different things like extragalactic objects or the moon.
Yeah. Okay, so we were talking earlier about your planetologist brain and wanting to look at other places. Asteroids for sure. Are there specific asteroids that you want to look at that you're like, that one right there? And then how do you go, that one?
So actually, I'm not an asteroid person. I have brought in a collaborator from NASA Ames. Her name is Maggie McAdam. She's put in a proposal to Sophia to look at these asteroids, and she's the one that picked out a couple of them. I'm not an asteroid person, so I can't remember the names of them.
No, that's fine. So, but she does. She's like, this one's a good one. It's like picking fruit, I would imagine. Like, this one looks right, this one doesn't. Okay.
Yeah.
And then how does that work? Does she read the article and go, oh my God, I bet there's water on asteroids. Let me send Casey an email?
So she actually was already working with Sophia looking at asteroids, but in a different wavelength range. And then when we did our observations, she was brought in as being like a guidance kind of for our observations and also for navigating NASA communications when the full press release was coming out. And so we got to talking and about what observations she does, and it just kind of came up with the idea maybe that asteroids do have water as well.
This is a good point to bring up too, because I'm curious, and from talking to Nicole, who works there as well, NASA is a massive organization, and it is a wide array of disciplines. Things like you're not going to the moon. You're not an astronaut. You're a fellow, a researcher. So how challenging is it to navigate through? And I'll say bureaucracy because that's what it is, but to navigate through all the channels to get what you want. And let me set the stage for this. One of my former commander in Bosnia, we were all spies. He and his team discovered the Al Qaeda attackers before 9/11, but they were so off into the side corner of this back office down the hallway around the corner. When they published their paper, no one read it, And so it's like, how do you avoid that? How do you elevate your message? How do you work through the machine? I mean, it's incredible that we all get to do this, but it's got to be, you have to spend a lot of your time navigating that institution, I would imagine.
Yeah, so what actually happened was we made this really large discovery, and we told some people at Sophia, we're like, hey, we found what we were looking for. We found water. We're writing a paper. We're going to submit it to, we were thinking one of the large journals like Nature Astronomy, and they were like, this is really cool. This is something that Sophia has never done before, and it's a demonstration of the Sophia capabilities. And so the NASA Sophia Communications Office, they wanted to run with a story. And that's kind of where things just kind of took off. And you never know with NASA press release or any press release, it could be a big hit or it could flop. And it turns out that a lot of people were really interested in it, and it was a big hit. And I think part of that has to do with it being the moon. It's something close to home. It's something people see every night in the night sky or in the morning sky. And so it's something that is close to people's hearts, and so people were very interested in it. So I think while it was interesting on the science side, the public side, it's just something that everybody can relate to.
Yeah, I mean, you literally look up and go, "There's water up there." I mean,
yeah, exactly. It's not yeah, it's not like some far out asteroid and we discovered water. People would be like, "Okay, that's cool, but I can't see that with my naked eye every night."
Yeah. When Nicole was on, Nicole Colon, I don't know if you know Nicole Colon, but we were talking. I'm like, you guys got to get better at naming planets. I get it that you're finding them at a pace that you can't do, and you'll run out of Greek and Roman gods. But calling something, Glessi Alpha B2,
yeah.
It's just not very exciting. So I wanted to ask too about, okay, so you navigate through the NASA things and they find the stories that are important. By the way, NASA, just for everybody listening, is fantastic to work with. They've been so wonderful in helping me tell these stories. But there are like you said, there are so many discoveries, rocks raining on this planet, life on Venus. These are all things that have happened in the last few months. Do you feel competitive with all of these different, and it's such an exciting time. It's like this discovery, on and on.
I think there's obviously some competitiveness that goes on because you want your research to be, at the forefront. You want people to be interested in your research, and you want to share that with people because outreach and educating the general public is important. At least to scientists, it's important. And so I think while there's some competitiveness, there's also this, yes, we're pushing the limits of science. We're showing people what we can do. We're presenting it to the public. And I think that in any aspect, that is great.
Yeah, it is really neat. And I appreciate you guys doing this. How does this discovery, and this is the question we always have to ask, right? Like, this stuff is expensive. We've got it, granted, a used 747, but I bet that thing isn't cheap to operate. So how do we take this science discovery and apply it to day-to-day life or make it valuable for humankind?
Yeah, so that's an interesting question. Everything that we do is kind of expensive, and the taxpayers pay for it. And that's why I think educating the general public is really important, is because you guys pay for my salary. So I have to, if I don't tell you what I'm doing, then I'm not doing my job. Right. But putting that aside, it's important for us to continue doing science because it advances our knowledge and our need to explore. But also, if, let's say, during the Apollo era, when they built the spacecraft and they went to the moon and they came back, a lot of that technology was fed directly back into the community. And the same thing is happening now, maybe at a slower pace than that during the Apollo era. But NASA does advances technology that can directly go back into the community for everybody to use. And that's why it's important for us to continue pushing the boundaries, to continue expanding our knowledge, to continue pushing the limits of technology, to further it so that it can come back to the general public and you can use it for your everyday lives.
Yeah, that makes a lot of sense. And there are so many ways that are unknown now that will be in 10 years. You're like, oh, yeah, this is one piece of that puzzle for sure. I know we talked a little bit about like wanting to look at asteroids and everything. What kind of money does it take to update? I mean, I'm sure you want to make changes to your machine or build a new one and everything, but what kind of money are we talking about to do this from now until Nature publishes the next article? What do you think?
So right now the Sophia plane is actually undergoing some maintenance, some routine maintenance in Germany. So they're updating the plane. They're making sure everything is working fine. I actually don't know how much that all is costing. I know that the Sophia plane costs a lot of money, but you know, the scientific discoveries that it does make and that it can make, I feel at least are worth it. But for me personally, I have to request grants that are upwards of thousands of dollars, hundreds of thousands of dollars in order to support the work that I'm doing, the team, the materials that I need, and also to support collaborations with other people. So it's quite a bit of money.
And then again, that's competitive too, right? Like you're all coming in. And so someone must sit above you and say, hey, Casey, that's just going to be too much money. I mean, that must happen, that conversation. And you all sit around the table and you're like, I'm going to need all of the budget this year. You know?
Yeah, we definitely have to work on our budgets, and we pay close attention to them to try and make sure that we make the most of the money that we are requesting, that it's going exactly where it needs to go, that we're not requesting more than we need or too little for what we want to do for the materials and the labor. But yeah, it's not an easy process, and there is a lot of competitiveness that goes into it.
I like to spend time on these aspects of it because it's not just astronauts going into space to the space station. There's so much going on, and there's, you know, all of this control over how do we do this, what decisions we make, what machines are we going to build. You know, there's just a lot in this, and it's just incredible to still see all this discovery outside of your specific discipline. What excites you about what you're seeing, other work that you're seeing that your peers are doing?
You know, I think what's really exciting is that a lot of my colleagues are currently pushing for research that the Artemis program is going to support, or that they support the Artemis program. So we're doing research on field instruments that astronauts could use during an extravehicular activity. We're looking at how rovers can look for water or ice or other useful minerals or volatiles on the surface of the moon. You know, people are working on the spacesuits for the astronauts to keep them safe, the habitats that they're going to live in, the oxygen that they're going to breathe, the water cycle that the space station is going to recycle for them to survive with, and the food and the research that has to go into the food. You know, there's so many aspects of research that go into the current Artemis program to make it possible that I think all of it is very, very exciting.
Yeah, and there's a lot of exciting things. And then do you see yourself staying in the solar system for the near future and studying water, or are you going to go adjacent to water and look at other things?
Yeah, so right now I'm hoping to stay focused on the moon and asteroid aspect of things. I thought about expanding to exoplanets, but I need to collaborate with other colleagues to make that one come to fruition, because that's not my area of expertise. But for the foreseeable future, I'm hoping to continue working on water on the moon and really characterizing it, understanding where it is, how it gets to the moon, how it's stored, if it's transported on the moon, and really place that puzzle piece together for future observations and research.
Does anybody come to you and say, hey, this seems like a question you can answer, and then work with them on a new project? Does that happen?
All the time. We try and make collaborations with people all over the world, from different agencies, different universities, and people approach me, scientists, my team, all the time with new ideas on what we can do with the observations that we're conducting right now.
And I don't want to have a political conversation, but how does policy and the people who lead it, how does that impact what you're doing? Because it's a fair question. It doesn't matter who's in charge, but how does that impact your day-to-day work?
So my day-to-day work doesn't vary very much depending on who's leading the office. What does change a little bit is the direction of NASA, but luckily right now, NASA has a very bipartisan agreement on both sides. So we're hoping that because of that, the work we're doing isn't going to drastically shift no matter who takes office.
I mean, what about internationally? How is the collaboration and who are really great partners that you get to work with?
So I actually haven't worked with very many international partners yet. I'm hoping to expand that to some international partners in the very near future. So it really depends on how NASA and the other European is mainly, and Japan are some of the big ones, that how well we play together. And we have really great connections with them right now, and I don't see that changing no matter what happens politically, because as scientists we like to try and keep politics out of that as much as possible, so we maintain our research friendships in good standing.
If budgets weren't a requirement, like if you were, all of a sudden in charge of NASA, where would you want to spend the money for what you do? Like things that you can't have, like anything you want, no budgets, no. Jeff Bezos says, "Hey, listen, I'm tired of my thing. I want to give you all this money." What would you do?
I think for me personally, there's two areas that I think are really important, and that is continuing human exploration, whether it's to the moon, to Mars, to any other planet or body in the solar system. I think that's something that we need to continue doing because, like I said, the technology that we develop for those programs feeds directly back into the public. And then also, I think it's important to continue earth sciences because Earth is our home. It is our planet. We need to understand it to the best of our abilities. We need to be able to protect it and take care of it. And so to me, those are the two areas that I would distribute the money.
Yeah. And then you have 3 other papers that we really didn't discuss at all. What stands out from any of those? We don't have to get into depth, but I mean, I want to celebrate what you're doing because you were so prolific this year. So talk about some of the other papers.
So one of the other papers that I had was actually using the NASA Infrared Telescope facility on Mauna Kea in Hawaii. And that was kind of doing the similar work of looking at water and how it might moves in its distribution on the surface of the moon, except for that wavelength range was the combination of molecular water, like we like to drink, but also its close cousin hydroxyl. And this is where my question of why can't we detect water kind of stemmed from and what led me to using SOFIA. That work I published, and I was able to definitively say for that work that whatever kind of water or hydration is present on the surface of the moon is moving and varying on the surface with temperature and time of day on the sunlit surface of the moon. And then another one that I published was that instrument that I built looking at volcanic carbon dioxide, which, it informs us about volcanic safety hazards. Hopefully in the near future, they can begin to take some of those kinds of instruments and predict volcanic eruptions based on the gases that are being emitted, which would be an amazing step forward in volcanology because that's never been able to been done before. But I think with monitoring the gases, they might be able to find precursor signatures of a pending eruption. But also, if you can put that instrument that I built and onto a small satellite orbiting the Earth, you could also look and monitor fires and predict the path of the fire and be able to do earlier warning systems and safety hazards.
Wow. Yeah, that's incredible. I mean, did you know that you were a hobbyist in the volcanology world? I can barely say the words.
Yeah, I didn't actually expect to ever do volcanology when I was starting out as an undergrad. So I'm really glad that I got the opportunity to work on something totally different from what I had expected to be doing.
I want to take a few minutes and just sort of talk about you and your background because, we have these unrealistic expectations of, like, in the arts, like, you never can make money in music. You absolutely can. There's a path, and it's challenging. It's impossible to become a part-time volcanologist / planetologist who discovers these incredible things. And especially for those ladies out there that are like, I want to do something in science. What does that look like? I mean, how do you look at you? You're a fellow for NASA at the Goddard Center. I mean, it's incredible. What does that look like?
Yeah, so I struggled to get here. I am actually diagnosed with dyslexia. So as a first grader, I was held back in first grade, and I had to repeat it because I couldn't read or write. And when I did write, I wrote everything backwards. So I, went through tutoring and a lot of schooling and extra work and a lot of hard work to get my grades up to really be able to function well in school on my own. And so, for a long time, I didn't expect to be able to go into any kind of science. I was honestly thinking that I was going to be some kind of artist, some performer, a dance performer or something. But then, my sophomore year of high school came around and kind of changed things for me. I no longer needed to be tutored. I no longer needed the assistants in school. I started taking science classes, and I really enjoyed my science classes. And that kind of turned on the light bulb of, hey, I want to go to college and I want to study something related to physics. And when I got a little bit further, it turned out that I wanted to do astronomy. And so I went to college for astronomy, and I didn't do too well in my first 2 years. I struggled really hard. It was not an easy transition. And so, I transferred schools. I went to a better program. I worked hard. I made a group of friends where we studied together and we worked hard together. We supported each other because, your support system is extremely important. If you don't have that, you're not going to get anywhere in life. And I, worked hard. And then when graduate school came around, that's where I really had to decide where my path was going to go. Am I going to go astronomy? Am I going to go computer science? Am I going to go research in physics, or what am I going to do? And that's what took me to volcanology. And, your path to get somewhere is never going to be consistent. But what is important is, one, your determination to get there, to wherever you're going to go, to follow what your heart is telling you, what you like to do. Because if you like to do it, it's not work. And then also just the determination and the drive to do it.
So it was easy.
No. Definitely not easy.
Yeah. It's because it always appears easy when you don't see the whole background work. That's why I love that question and all the things that go into it, because it isn't easy. What is, when you're doing it, when you're really working and feeling the pressure and running a team and everything, how many hours a day are you putting in on this? Whether it's clocking time with your brain as you do something else, or what is that like in terms of the workload?
I really strive to have a good work-life balance, because I know personally that if I don't have that balance, that I'm not going to do well at work. And so I usually put in between 40 and 50 hours a week of work. Some weeks that picks up and I'm working from 8 a.m. till 10 p.m. and I go straight to bed and I get up and do it the next day. It really depends on what I have going on. If I have a proposal that's due tomorrow, then I'm probably staying up until 3 a.m. finishing it. If I have a presentation in a week, I'm spending the entire week working on the presentation, practicing it many, many times and reviewing it, memorizing it. And it just depends on what's happening at that time.
Again, like the whole peer review process, like to have the proper literature review in there, and to have a pretty good mastery of what's already been done, so you don't miss something, because that's just, there's so much work to do. And then, and if you're like me at all, sometimes just unplugging and getting away from everything and going for a walk, workout, nap, whatever it's going to be, my brain will put the pieces together subconsciously, and I'll come back and be like, oh my God, I figured this whole thing, I have, a new idea, a new things to do. Do you work like that?
It's actually kind of funny. I do work like that, but only when I'm sleeping. I will be asleep and I will code in my brain, and then I'll wake up and all of a sudden I'm like, oh, that's why my code's not working. Let me go fix that. It's the strangest thing.
I would take a nap all the time in Afghanistan working, and I'd be like, okay, I'm gonna take a nap and see what I come up with. And
Yeah.
it was legit work. And I would come back and I'd be like, I figured all these things out in my sleep.
Yeah.
You know? It's so incredible.
Who knows when you're trying, when you're not trying
Yeah.
to think about it.
Yeah. But can you sustain that level of work that you're at? Are you work-life balancing? Do you feel like you're doing it, or are you like me? You're like, it's for me, it's more like work-life integration. I'm always trying to balance it. I always have to tend to it, because if not, I default to overworking.
You know, I feel I worked a lot when I was a grad student, and I feel like that kind of, it didn't burn me out, but it made me realize how important my life balance part is. And so when I moved to my fellowship, I was like, okay, I'm going to work the hours that I need to work. I'm going to get my work done, but I'm not going to let my work drive my life anymore. It's not going to be the driver of everything. You know, I'm going to have dinner with my husband. I'm going to go to this event with him on the weekend, or whatever it is, you know, or if I have chores to do around the house, I'm going to go do my chores, you know, because sometimes those things, getting those things off your brain, off of your mind, and out of your subconscious helps you work better. And I feel more productive now than I did when I was a grad student, trying to make these long hours happen and, you know, make my dissertation come to life.
Yeah. There's an elegance that we all have to develop with what we do, because you can't just, like, when people say train more, work harder, like at some point you've done it all. Like there is no more, like I always say, like the recommendations always work harder, you know, like no, at some point you have to, you know, I don't do that. Right.
More than 100%.
Yeah, exactly. Well, listen, I think the world of you, and I love what you all are doing over at NASA, and it's so exciting. And I love that Nature and all the other, you know, peer review magazines are out there just kicking out all these great things, because, you know, the world is really changing. I can't even imagine 10 years from now how all of your guys' combined work is just going to change how we live, and for the better. I mean, all you have to do is look back 40 years and go, wow, world's a totally different place, you know? I just love it. I love what you guys are doing. I love that NASA's telling stories. You guys are all so wonderful. Thank you so much for coming on the show. Anything you want to say to all the millions of people that are out there, like, hey, I love space. What do you want to say?
You know, I think the most important thing is to find something that you love to do, no matter what it is. If it's science, art, relationships, no matter what, find something you love to do.
Perfect. I love it. Okay, stand by. I'm going to shut this thing down. Hang on one second.